the Born-Haber process. What it does is it measures, as stated above, the lattice energy. So how much energy is released when an ionic compound forms a crystal lattice. So to understand the process, the goal of the process is, in order to measure the lattice energy, the process is get the reactant to the ionized gas phase. Ionic compounds are composed of ions, and the lattice energy is measured whenever you have ionized gases combined to form an ionic compound. So, for example, if we have magnesium solid reacting with diatomic chlorine, gas phase, they react to form magnesium chloride. You may recall this from earlier in your chemistry experience, that this particular reaction, when you have elements in their standard states, magnesium metal exists as a solid in its standard state, chlorine in its standard state exists as a diatomic gas. When they react to form 1 mole of a compound, that is an enthalpy of formation. Back from chapter 5 or 6, chapter 5 from the OpenStax text. So that reaction. So this reaction has an enthalpy value and energy is released. But what is the energy associated with the crystal lattice when this ionic compound forms? So the goal is get the reactants to the ionized gas phase. So to go from magnesium solid to magnesium gas, that requires energy. That chemical process is sublimation. So a solid going to a liquid would be melting, a solid going to a gas is sublimation. So again, the goal is getting the elements to the ionized gas phase. Right now, magnesium is in the gas phase, but it isn't ionized. It still has its valence electrons. So if you look at the magnesium and magnesium chloride, its charge is +2. You look at the periodic table, magnesium's in group 2, it's got a +2 charge. So that means that this magnesium has to be given a +2 charge. So ionize once. First ionization energy, the magnesium is ionized to become magnesium plus. Make myself some more room. It has to be ionized. The second ionization energy, again, the gas phase. So magnesium 2+. So magnesium 2 plus is ready to react to form the crystal lattice. It now has the same charge as the magnesium in the product. So, for chlorine, here it's a diatomic molecule, a diatomic element. Here it's two individual chloride anions. So this molecule has to be broken apart. It has to be split into monoatomics. So that energy is the bond energy of the chlorine-chlorine bond. Energy's got to be put into the molecule to convert it into two chlorine gas molecules. Chlorine, in this form, is uncharged. It's not an ion. In our product, it has a -1 charge. Okay, there's two of them, each with a -1 charge. So the ion that needs to form is chloride, Cl-. 2 moles of it. 2 moles, it's balanced, 2 moles. Those 2 electrons come from the ionization. Magnesium gives the chlorine the electrons. Combining these terms, you've got magnesium 2 plus 2 electrons plus the two chlorine atoms in the gas phase. So the chlorine atoms are going to get the 2 electrons. So you still have magnesium 2 plus, gas phase, plus 2 moles of chloride minus in the gas phase. And what that is that is 2 times the electron affinity for chlorine. The reason it's 2 electrons, 2 chlorines, so 2 electron affinities occur. Now, the goal has been reached. Ionized gas phase for magnesium 2 plus, ionized gas phase for 2 chloride anions, Cl-. That is the lattice energy. The energy associated with the magnesium and the chloride combining to make this product. So that's what the lattice energy is. Hess's law is still true, meaning that if you did this reaction in one step, that has an energy value, and this energy value is going to be equal to this step plus 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 this step. I know it's a lot, but let's list them. This is all still true. The enthalpy of formation, one step, is going to be equal to the enthalpy of sublimation from the magnesium plus the ionization energy from magnesium plus the second ionization energy from magnesium, plus the bond energy from Cl2, plus 2 times the electron affinity for chlorine, again 2 times because you have 2 moles of monoatomic chlorine reacting, plus the lattice energy when that crystal lattice forms from the ions in the gas phase. 1 step, or 1, 2, 3, 4, 5, 6, because it happens twice, 7 steps. And then to solve for this, you subtract all of this as one term from both sides of the equation. The lattice energy is equal to the enthalpy of formation minus, put that all in one term, that equation. So subtracted all of these terms from both sides of the equation to solve for the lattice energy. Conducting a lattice energy calculation, usually you're giving a table of information about all the various steps that we went through in the previous slide for the Born-Haber process. And it becomes a matter of just identifying which of these energy values correspond with the chemical process described. Right, so, let's just start. So the enthalpy of formation here, that's the equation. Magnesium solid, diatomic chlorine, so elements in their standard states making the compound. That's the enthalpy of formation value for this term. Sublimation. Magnesium solid to gas. That's that process, that reaction. Solid to a gas is sublimation. That energy value. (147.1 kilojoules per mole). Next, first ionization energy for magnesium is here. Magnesium to magnesium plus. That's the value. Just go ahead, ionization energy 2, we'll need that. Magnesium plus to magnesium 2 plus. Those are ionization energies 1 and 2. IE1 plus IE2. So magnesium's in the gas phase, the ionized gas phase. Next, chlorine to break it from diatomic chlorine to monoatomic chlorine, that value. Next, the chlorine. It's monoatomic, becoming an anion, chloride. That's an electron affinity, but it happens twice. We have 2 moles of chloride in 1 mole of magnesium chloride. So 2 times negative 349 kilojoules per mole. In all terms. If I do all that math, minus the term, the complex term, 1881.1 kilojoules per mole, and then all of that you get the lattice energy to be minus 2,522 kilojoules per mole. Four sig figs, that's what it would be. And that's how much energy is released when a magnesium chloride crystal lattice forms. And that's an example of the math. It's a lot to keep track of, but the key is to associate the enthalpies with the correct chemical process in order to be successful.